We generate massive amounts of raw electrical energy at distant power plants, but we cannot plug that power directly into the homes and industries that need it without some extreme manipulation. To bridge that geographical gap, we rely on the power transformer. This static device steps voltage up to incredibly high levels so it can travel efficiently over long distances, and then steps it back down so it's safe for local consumption. Because of the sheer amount of energy they handle, these machines are massive. As you can see in this photograph, a single unit often requires a specialized multi-axle transport vehicle just to move it. They are routinely the largest, heaviest, and most expensive singular components on the entire electrical grid. But unlike a standard car engine, which only operates at roughly 20% efficiency and relies on thousands of moving parts, a transformer is completely static. It has zero moving mechanical parts for its primary function, yet it operates at an astounding 99.5% efficiency. It's this precise combination of massive physical scale and quiet, extreme efficiency that makes an interconnected modern electrical system possible. To understand how they work, we start with Ampere's law. Whenever an electrical current passes through a wire, it naturally generates an invisible magnetic field in the space immediately around it. If we take that straight wire and wrap it into a tight coil, what engineers call the primary winding, we concentrate that magnetic effort. The scattered field lines merge into a strong, directional beam of magnetic flux, pushing right through the center. Next, we introduce a core made of high magnetic permeability steel. Because magnetic flux naturally prefers to travel through iron rather than open air, the steel core traps the field, guiding it smoothly around a continuous closed loop. According to Faraday's law, if we wrap a second, separate coil of wire around the opposite side of that iron core, the moving magnetic flux passing through it will induce a brand new electrical voltage in that second circuit. The exact ratio of the input voltage to the output voltage is dictated entirely by a simple geometric relationship, the number of wire turns in the first coil compared to the second. If the secondary coil has exactly half as many turns, the voltage drops by exactly half. In an ideal theoretical universe, this perfect magnetic loop scales power up or down flawlessly, with zero lost energy. But electrical engineers do not work in an ideal universe. They have to build practical machines that survive the harsh physical realities of high-voltage transmission. The first problem is leakage flux. No iron core is perfectly efficient, meaning some of that magnetic field inevitably escapes into the surrounding air. This creates an inductive resistance that forces the system to work harder. Then there is physical degradation. The natural resistance of the copper wiring causes copper losses, while the rapid, constant reversing of the magnetic field in the steel causes iron losses. Both of these inefficiencies manifest as massive amounts of waste heat. To keep the unit from destroying itself, the internal components are submerged in specialized insulating fluids. In this technical image, you can see the solution engineers use to manage that thermal energy, an extensive exterior array of circular cooling fans and radiator piping. On top of the heat, engineers have to deal with a grid that constantly fluctuates. The perfect, fixed mathematical ratio of those copper coils often needs to be adjusted while the machine is actively running, just to keep the voltage steady. To do this, they install internal mechanical switches, known as tap changers. These mechanisms dynamically add or subtract active turns from the winding, allowing operators to precisely dial the voltage output up or down on the fly. A modern power transformer is a complex thermal and mechanical battleground, meticulously engineered to preserve magnetic harmony against the constant friction of real-world physics. Because grid demands vary wildly depending on the location, that basic core and coil architecture gets radically customized for specific jobs across the network. This technical photo shows an interconnecting autotransformer. These act as massive bulk transfer hubs in the transmission yard, linking completely different high-voltage networks together, like bridging a 500 kilovolt line directly to a 240 kilovolt line. Inside these autotransformers, there is often a hidden tertiary winding. This is a third, unloaded coil specifically designed to absorb and stabilize dangerous harmonic frequencies that bounce around the grid. When we look at renewable energy infrastructure, the demands change again. High-voltage direct current converter transformers require intense, specialized insulation to survive both alternating and direct current stresses, a design requirement that makes massive offshore wind farms viable. We even shrink the technology down to the consumer level. Here we see the pantograph mechanism connecting the roof of a train to overhead wires. Inside the train, a specialized locomotive transformer takes that immense voltage and steps it down to a level that safely drives the electric motors. Power transformers are dynamic, highly tailored energy translators. They are the essential physical link that allows us to harness raw electrical power and shape it into a reliable,